Welcome to this BioExcel video tutorial about the BioExcel Building Blocks Pre-Exascale Workflows. My name is Adam Hospital. I'm coming from the Institute for Research in Biomedicine in Barcelona, and I'm coordinating the Workflows division in the BioExcel Center of Excellence. The idea of this video tutorial is to present you the work that we are doing in the BioExcel Center of Excellence in building biomolecular simulation workflows, able to efficiently use thousands of cores from HPC supercomputers, and that is in preparation for the imminent availability of the pre-exascale supercomputers. And also to show you or to let you know that these workflows are already available and openly available to any users of the MareNostrum4 supercomputer here in the Barcelona Supercomputing Center. And we have plans to install them in different European supercomputers, but now they are working on the MareNostrum, and I will show you in this video what these workflows are capable of and how can you use them and play with them in a very easy way using just a MareNostrum4 account. Just to start with, I will start with a brief introduction on the BioExcel Center of Excellence. This Center of Excellence started as a project, as an European Horizon 2020 project in the year 2016, 4 years ago, with the motto of becoming the central hub for biomolecular modeling and simulations. And for that, more than 15 European partners joined together, coordinated by the KTH in Sweden, to work on the connection of life science and HPC in this area of expertise, from small molecules, macromolecules, and reaching the cell unit. And the main objective of BioExcel is enabling better science, mainly by these three important points: improving the performance and functionality of key applications, providing support to non-experts and advanced users, and developing user-friendly computational workflows. As you can imagine, we are deeply involved in this third point, the user-friendly computational workflows. But let me introduce really briefly the first 2 points. So the key applications that we are working on, improving them and making them more efficient every day is the GROMACS package. They are all really popular biomolecular simulation tools. GROMACS, as you can see, GROMACS for the molecular dynamics, PMX for the free energy calculations, HADOC for the protein-protein docking, protein ligand, and protein DNA too, and CPMD and CP2K for the QMMM and QM calculations. We have also a part for the support. We have webinars, training events, conferences, workshops. We also have a forum where you can ask every question that you want in the ask.bioexcel.eu webpage. And we have we are also visiting industry companies. But the main focus of this presentation, of this video tutorial today, is the workflows. We are designing, deploying, and making available biomolecular workflows with two important points in mind. We want them to be really usable, so really easy to use, available, reproducible, being able to be used in different platforms, different infrastructures, and for that, we are working together with Elixir, pushing for best practices in software development. And the second point, and that's why we prepared this video tutorial today, is that we are really interested in designing and developing these workflows prepared for the exascale. And when I say exascale, I mean that this exascale computing, that refers to computing systems capable of calculating at least 10 to the 18 floating point operation per second. That's a lot, and why this is so important for us, and this is basically because this is the #1 supercomputer in the top 500 list as of today. This is the Fugaku supercomputer, and as you can see here, it has more than 7 million cores. That means that we should be prepared to use thousands of cores in one single job for the new HPC supercomputers that are appearing right now. And even more, the European Union is leading the way in this supercomputer and has pushed that with €1 billion to build pre-exascale machines, 3 pre-exascale machines with more than 150 petaflops, and different petascale machines in Europe, and actually in the Barcelona Supercomputing Center, we are going to build the new MareNostrum4, which is one of these pre-exascale machines that will have lots of cores, maybe such as this one. I don't remember the number exactly, but millions of cores to be used in research. So we should be prepared for that. And I will want to show you our approach in BioExcel to deal with this pre-exascale supercomputer. We are using a framework that is called PyCOMPSs that is developed in the Barcelona Supercomputing Center. And this framework is able to, just looking at some script, in this case, for example, is a Python script, automatically identify these loops like this one. If you can see, it says for every mutation in a list of mutations, do something, and PyCOMPSs is able to automatically recognize that, transform that to a graph, and a cyclic graph like this one with all the dependencies. And this is transformed basically to different branches that are launched in the supercomputer completely in a parallel way. This PyCOMPSs also has fault tolerance of some of the branches. If any of the branches fails, the rest of the branches will continue the execution. Of course, if there is a dependency at the end that needs all the output of the rest of the branches, this is not working. But if there is no dependency at the end, this fault tolerance is really important. Imagine if we have like 20 different molecular dynamic simulations and just one of them crashes. We want the rest of them to reach the end of the simulation. This is what we call the embarrassingly parallel executions, but you can see here the efficiency of in the CPU usage in the MareNostrum4 supercomputer. You can see that all the nodes are working 100% of usage, except the one that is the master execution for the PyCOMPSs framework. So we are reaching really efficient regime using this PyCOMPSs framework. We can also use an efficient usage of resources, like in this case, when we have a higher number of executions, much more than the number of nodes available in the machine for our job. So this is a real example of a protein-protein benchmark using Hadoop. This is 200 different executions in Hadoop with just 50 nodes of MareNostrum, more than 2,000 cores. And you can see here that when one of the execution has finished, automatically another execution of Hadoop is launched by PyCOMPSs, automatically identifying that from the Python code. This PyCOMPSs is how we control the workflows, but how we how we build these workflows. We are building these workflows with the BioExcel Building Blocks, which is a new software library developed within the BioExcel project, which is an interoperable biomolecular simulation workflow library. I will not explain you in detail the BioExcel Building Blocks, but just really briefly, the BioExcel Building Blocks is a Python wrapper library, which is each of these building blocks is wrapping a biomolecular simulation tool and is giving one single functionality. These different functionalities can be really easily integrated one on top of the other. So this is because these wrappers are offering a higher level of interoperability. And once we create these workflows, then we can launch these workflows using different workflow managers, graphical interfaces such as Galaxy or KNIME or Jupyter, but also HPC-focused workflow managers such as the PyCOMPSs previously presented. You can find many information from the BioExcel Building Blocks in the paper here, Nature Scientific Data, in the website for the BioExcel Building Blocks. You can find also webinars, tutorials, and different videos on the YouTube channel on the BioExcel. As a summary of that, we are building our workflows with the BioExcel Building Blocks, and we are controlling them with PyCOMPSs, making them really efficient on HPC supercomputers using thousands of cores in one single job. And this is important, the workflows are very easy to adapt and customize. And I will show you examples of that in this video tutorial. How this works, it is really easy. What we have in our workflows is they are separated in two different pieces. The first one is the workflow script in Python language. So you have the Python code with all the building blocks that you want to use. Here you have, for example, a typical MD setup where we download the PDB, fix the sidechain, generate the topology with GROMACS, generate the box, solvate the box, start with adding the counter ions, start with a minimization of the system, etc. This is a sequential and very easy workflow, but all of these are different building blocks. We can have also loops and conditionals and make the code a little bit more difficult like this than this one. And then on the other hand, we have the workflow parameters. So that means all the inputs that the workflow needs, all the outputs with the dependencies on the different steps. So if the third step has a dependency on the second one, on the output of the second one, this is stated in this YAML file. And of course, all the properties, that means all the parameters for all the different building blocks. That means that the code is never modified, but the YAML file, these workflow parameters are the ones that you should modify when you are interested in running one of these workflows. As I was telling you before, if we are launching that using PyCOMPSs will automatically recognize these lines like this one with the loop on a set of mutations. As an example, here in the YAML file, we will have 3 different mutations. Here in the Python code, PyCOMPSs will identify these 3 loops in this loop and will launch 3 different branches in parallel of the execution. So this is the first example, an easy example. This is a molecular dynamics setup and run for a list of structures. Remember, we have a Python code and a YAML file. This is the workflow, really easy. For each PDB from a list of PDB files, we are using GROMACS, of course, because it's one of our key tools in BioExcel. We generate the topology, minimize the energy, equilibrate the system, and run the molecular dynamics simulation. Here is how the Python code and the YAML looks like. Here you have the loop on all the structures from the input structures that PyCOMPSs will recognize, and here we start working with generating the topology, the box, solving the box, etc. And here we have the information on the parameters. Those are the 4 different PDB structures that we want to simulate. And here we have the first step, which is generating the topology. We are stating here that we want to do that with a particular force field, which is the number 99 SB ILDN. When we generate the box, we want an octahedron box with 1.2 nanometers of distance to the molecule, etc. So you can see that here we have the parameters and the input files and the dependencies, and here we have the code. This is important, but you don't need to remember that because we are building a library of workflow templates for you. So this is the first example, but of course we are working on different templates. For example, want to model mutations on a protein and then run the setup and the simulation. Now want to compute free energy calculations. We are going to see and work a little bit and play a little bit with these examples today in this video tutorial. We are working on virtual screening and many more workflows using the BioExcel Building Block. On top of this library of workflows, we are generating also the workflow launchers. And we are making that mainly because depending on the machine that we are running this, on the HPC supercomputer that we are running this, the environment modules that we need can change. So just as an example, for the MareNostrum4 supercomputer, this workflow launcher will generate this file which will load the modules needed to run a particular workflow, for example, Anaconda and BioDB. In this case, to start with, also a PyCOMPSs package, then the Singularity package, because we are using Singularity to run the PMX code, then the GROMACS molecular dynamics package, and finally the specific run parameters. That means that in the workflow launcher, we can state, for example, the length. If you think about the molecular dynamics simulation, we can state the length of the simulation, the type and the size of the box system, etc., and the force field, these kind of parameters. for the workflow. And finally, it will generate a shell script, which is the one that PyCOMPSs is understanding and launching. This is enqueueComps with some parameters, and finally the Python workflow and the YAML workflow, which are the two files in our template. Of course, modify it depending on these parameters here, especially these ones here. For example, this is for the MareNostrum4, but if we go to the French CEA HPC center, we should modify the load, the module for the BioDB. We should modify also the load for the modules for the Singularity. They are not compatible with Singularity. They are compatible with Docker through another library that is called PCOCC. This is just an example of how we are modifying the launcher to be able to execute exactly the same workflow, because this is exactly the same template, but in different machines. And I will show you examples of this launcher in this tutorial. So let's go to the examples. We have generated the GitHub repo with HPC workflows in BioExcel. This is a part of the README file that you can see there. Information about the template workflows here at the beginning, and also information about the launchers here at the end. We will start with the first one and the easiest one, the molecular dynamics list that performs the system setup, runs molecular dynamics on each one of the structures listed in a file, in an input file. We have a launcher for that, which is called MDLaunch, and I will show you now the reality. This is the reality. This is the MareNostrum4, and this is how you could execute this pre-exascale workflow. It's as easy as that. Everything is prepared for you. You have many different input files to put, but only one is mandatory. It's really easy. This is an example. This workflow gets as an input this structure list. This structure list is a file that contains these 4 different paths to 4 PDB structures. And I'm saying that I'm interested in 100 nanosecond simulations using 16 nodes in the MareNostrum4. Each of the simulations I want to run in 4 nodes in MPI regime. That means that 4 nodes by 4 structures. It ends up summing these 16 nodes that I'm requesting in the queue. This is the output folder. This is the queue name. This is the work clock time, and it is the job name. So actually, the most important one is, of all of these parameters is the structure list, length of the simulation, and the number of nodes that you want to use. You're maybe wondering why or if this workflow is really useful for you, this kind of easy workflow. But if you think about the work that you're doing every day, you will find something, I'm sure that you will find something like this. This is our work that we published last year in our group. And I'm not going to enter into detail in the work that we did, but basically we wanted to study the flexibility properties of the different tetramers, and for that we DNA tetramers, and for that we generated a list of 13 18mers sequences that contained all the different tetramers here inside, and we from these sequences we generated the structures, and for the 13 different structures we wanted to simulate them with sodium ions, counter ions, with potassium ions, and with a mix of 50% of both. And we wanted to simulate them with PyBSC 0 and with PyBSC 1, 2 different force fields to study the differences between them on the results and on the flexibility. That at the end means that we had a lot of different molecular dynamics simulations to do. Of course, we split the work with the different authors of the project. But now, if you think about it, we could use something like that, put everything together, at least 13 simulations in one single job in one of these structures list files, and simulate them in one single job using 104 different nodes in the MareNostrum. For example, this is just an example, using 8 nodes in MPI regime for each of the simulations. And with just hours, we'll have all the molecular dynamic simulations for one of these groups. And of course, with 6 different jobs, we would be able to have all the simulations for the 2 different force fields. This is just an example, but I can think about another example also from last year. In this case, we wanted to understand how much of the information of the protein DNA recognition was encoded in the BDNA, in the canonical BDNA dynamics, and for that we selected 50 set of 50 protein DNA structures from different families from the PDB, and we simulated the DNA coming from these PDB structures, just removing the protein, and then we simulate the same DNA but from a canonical form. We generated the sequence in canonical form and we simulated them, and then we compared the results and see if the canonical DNA still had the information needed to properly bind the protein. That were 15 different molecular dynamics. If you think about it, it's 15 for the canonical, 15 for the DNA with the protein removed, and we also generated some of these protein DNA complexes and simulated them. Again, we can put everything together in one single job, 50 molecular dynamics for the 50 DNA structures using a lot, thousands of cores of the MareNostrum, but this is a possibility using exactly the same workflow as you see here. Exactly the same, just using 400 different nodes. And this is basically thanks to the PyCOMPSs framework. Okay, moving to a more complex scenario, more complex project, and that was something that we started, as you can imagine, during the pandemic. And I'm sure that I don't have to present you these images here. I'm quite sure that you will know what the virus is. This is the virus, the spike protein that you can see here, the RBD protein receptor binding domain that is moving away from this spike and is the one recognizing the angiotensin converting enzyme, which is the humanase that you can see here in blue, the membrane of the human protein. And basically, most of the groups are working on the interface of these two proteins, the RBD and the humanase, trying to identify what are the important residues for the infectious mechanism here. So this is exactly the interface, and this is what we are also studying by means of non-equilibrium alchemical free energy calculations, in this case of relative protein binding free energy differences. Again, I'm not going to enter into details about that. If you want to know more about this, if you are familiar, you will recognize these non-equilibrium calculations. If you're not familiar, please take a look at the PMX webpage from the Groth group. You'll have all the information there, and also in the book chapter from Vitas that you have here in the references. But basically, to compute these free energy values, we will need an equilibrium simulation for one of the monomers, in this case the receptor binding domain for the wild type, another one for the mutant that we want to study the differences or the effect of this mutation on the binding of the two proteins. And then we will need the same, the equilibrium molecular dynamics for the complex, RBD humanase in this case, for the wild type and also for the mutant. This will generate 4 different equilibrium molecular dynamics, as you see here. And then using these equilibrium molecular dynamics as an input, we will extract a set of frames from them and start short molecular dynamic simulation, thermodynamic integrations, one forward and one reverse, going from one state, lambda 0, so the wild type, to the mutant, lambda 1. And from all of these different short molecular dynamic simulations, we will start the work and we will get the intersection using Crookes' theorem. And we'll extract one of these delta G's, and once we have the 2 different delta G's, we can subtract them and obtain the relative protein binding free energy difference. All of this, which is really complex, is a complex workflow. We transformed in 2 different pre-exascale workflows. The first one is the, let's say, the easy one, molecular dynamic simulation data for each of the mutations. So we model the mutations and we run the simulations for the RBD system, for the ACE2 system, and for the complex. And using these simulations as an input, then we run the free energy calculation using another workflow, pre-exascale workflow, which is this one that you can see here, which contains the fast growth in thermodynamic integration. That means that a number of independent short molecular dynamic simulations, in this case we run 1000, but this is completely a parameter that the user can, of course, modify. This is done using GROMACS and PMX, and it's extremely parallelizable because all of these short-term simulations are independent. I'm not going to enter into details about this. We are exploring not just the SARS-CoV-2, but also other virus species, such as the bad one, and also different A's coming from other species. So this, at the end, is a big data study with different, that we need to appraise computational power for that, and we are computing a lot of free energies using these pre-exascale workflows and using thousands of cores. The template workflows are these two. So the first one, really easy, like the previous one that we have seen, but in this case we are modeling the mutation, and for each mutation we are running a setup of the simulation and the final production simulation. And for the free energy calculations, all of these different boxes with these free energy calculations in the middle, so a lot of work that at the end will give us the delta G that we need. So these are two different templates with the Python and YAML files, corresponding files. And you have all these workflows templates here. Those are the ones that generate the molecular dynamics simulation for the mutation. This one is modeling a mutation one by one. That means that from the wild type it is modeling one mutation, and then another mutation, and then another mutation, all of them on the wild type. And this one is accumulating the mutation. That means that from the initial structure we are generating one, and then two mutations, and then three mutations. And this is an accumulated, and this is how we are going from one species to another and identifying the effect of these mutations. This is the PMX free energy workflow template. And here we have two launchers, one for the generation of the mutations and dynamics, and another one for the free energy. And again, this is the reality. This is how we call the first of the workflow to model, set up, and run the molecular dynamics simulations in the MareNostrum. Here is one example, real example of an execution. I want to simulate the wild type. I want to simulate this particular mutation and this particular mutation. So three different molecular dynamics simulations. I don't want the mutations to be accumulated. That means that I will have a system with the wild type. I will have a system at the end with these mutations, and another one with just these mutations. And this is the wild type protein. This is the length of the simulation, number of nodes, MPI nodes, the same as before, nothing else. It's really, really easy to run this workflow. The second one, it might seem a little bit more complicated than the other one, but at the end it's exactly the same. What we need in this case as an input is the mutation that we want to study. And then, if you remember, we have two equilibrium MD simulations as an input. So the wild type is this one here. We need the topology and the trajectory. Those are two inputs. And then for the mutated one, we need the topology and the trajectory. So these two ones here. And then the number of frames that we want to extract to perform the forward and reverse thermodynamic integration, in this case 500. And the rest of the parameters, you already know them. The name of the queue, the name of the job, the output folder, number of nodes, and work clock time. Nothing else than that. Of course, there's more parameters that you can use, but those are the most important ones. Examples of the efficiency of these pre-exascale workflows and how they are able to use 100% of the CPUs of these many numbers of nodes that you can see here. So this is an example of the molecular dynamics of the mutations. 48 nodes, more than 2,000 cores in one single job. This is for the complex RDD humanase. It's a real example, 10 nanosecond length that we were able to run in just 8 hours using 100%, as you can see here, of the CPU usage of the 48 MareNostrum nodes. The PMX is also as efficient as the previous one. You can see here 100% of usage of all the different nodes except for the PyCOMPSs master, which is controlling the whole workflow. In this case, we were using 32 different nodes with 500 cores. This is just one mutation, 1,000 short thermodynamic integrations of 50 picoseconds in just 5 hours time. So it's time to go to the MareNostrum4 and try to play a little bit with them and see that what I have presented in these slides is the reality. So we go to the MareNostrum, and I will open a README file with all the information containing examples, such as the one that I was presenting you, that you can, if you have an account in the MareNostrum, you can just type and execute directly. You have the README file here, and you will find information. This is completely open to everybody, to every user in the MareNostrum. You have information about the collection of Pre-Exascale workflows from the BioExcel Building Blocks. You have 5 sections on this README file. Information about the library, the templates, information about the launchers, you already know that, and examples of use, that is an important one for us. So we scroll down, have information of templates, of launchers, and the example of use. There's a note here saying that the old workflows need the Python module previously loaded, so let's do that. Let's connect again here in another tab of the terminal, load the Python 3, as easy as that, and we can start working with the workflows. So the first example is launching empty simulations for a single structure, just a single structure. You can do that, of course. And for that, we have the lysosine protein as a test case. And here he's explaining a little bit what are the parameters that we are using. This execution uses 4 BSC MareNostrum4 nodes, which are 192 cores in MPI. Each of the nodes in MareNostrum contains 48 different cores. The length of the simulation is 5 nanoseconds, and the force field used is charm 27. Let me just copy the command line, try to execute it. Let's go here. I have prepared a folder for that, which is empty. I execute this. It's telling me that the job is submitted. If I look at the queue, I will find that this is the job. I have launched that in the debug queue in the MareNostrum, but let me show you just really briefly how the MareNostrum is right now. It's like that, so it's completely full. So I don't know if we will be lucky enough to see our simulations running even in the debug queue, but let's see, let's hope for that. In the meanwhile, let's check the command line, which is really easy. This is the launcher, if you remember from the presentation. Of course, you can put a -H here for help. There's a lot of information on all the different parameters, input structures, so the file with the list of structures to be simulated, 1 structure path per line. You can put the type of the system that you are trying to simulate. This is important for GROMACS, for the temperature coupling groups. You can modify the force fields. You have different options here, box size, box type, etc. Of course. There are more advanced parameters that you can modify, such as the GROMACS lib, the path where to find the force field libraries. If you want to modify to run a molecular dynamics simulation with a custom force field, you can also do that. Let's check the input file. Really easy. It just contains 1 line, which is the lysosine PDB, the path to the PDB structure. This is just the PDB structure, downloaded from the PDB directly. Okay. We have the name of the queue, which is the debug, the number of nodes, which is 4. In this case, I want to use 4 nodes for the simulation in MPI regime. That's all the nodes that I requested. This is the job name, work clock time in minutes, that's 2 hours, so it's the limit of the debug queue in the MareNostrum supercomputer. 5 nanoseconds is the length of the simulation. This is the output folder, and this is the force field. And this is running, so we were lucky, and we can see how this generates a temporary folder where PyCOMPSs is computing everything, a standard output and a standard error of the PyCOMPSs framework, which is the one that is controlling the whole workflow. And here we already have the output folder, which is the charm one. Here you will find the Python script, which is the, if you remember, the template that we have, but modified, not this one. This one is the one modified, the parameters file modified with the parameters that we put in the launch. So for example, this force field here, name of the force field, the length of the simulation, all of these parameters are modified directly to the template in this YAML configuration file. And in this Python, if you remember, we have the workflow. And the launch is the SH script that is using PyCOMPSs to launch the execution. This is the output of the workflow. Here you can see the lysozyme PDB, and inside the lysozyme PDB we have all the different steps, which are the building blocks that are contained inside the workflow. So the generation of the topology, generation of the box, solve rate of the box, etc., etc. So this is now working, and at the end of the day, we will have in this step 10, which is the last step, the production run, the simulation. So let's see another example. This is as easy as that, as you could see. Example 2, launching a simulation for a list, in this case of PDB structures. And this is the example of the mini ABC list, so the tetramer study of DNA. In this case, the list is formed by 13 nucleic acids, 18 mers containing all possible tetramers. 14 nodes of the BSC MareNostrum are used, so 672 cores in this case, one of them reserved for PyCOMPSs. So I'm requesting 14 nodes, and I know that we have 13 sequences, 13 structures. System box time, size, and ionic concentration are given as parameters, so this is the command line. And we copy and paste here. Again, I'm using the debug, which has a limitation of one single job in execution. So this will be staying here waiting until this has finished. And this will require like 30 to 40 minutes, so we will not see the output of the other ones, but anyway, I have them prepared for you to see the hierarchy of folders. In this case, anyway, the mini ABC folder is already created, but let's check first the command line. Again, really easy. This is the same workflow launcher as before. The input, we have now used this list of structures that you can see here. All of these structures are available for all the users in the MareNostrum system, because this is a folder that is open to everybody. You can take a look if you want at one of the structures, but basically is a DNA, 18-mer. This is prepared for Amber. The Q is a debug, the number of nodes are 14. Just one node per each of the simulation in this case. Remember, 13 simulation plus one, which is one node that is controlling the workflow with PyCOMPSs. The name of the job, the work block, the length of the simulation, the output folder, the system that we are trying to simulate, in this case is DNA. This is the box size, 0.7, this is in nanometers because we are working with chromats. This is the type of the box, and this is the ionic concentration. So nothing really complicated, and this will run, and I will show you an example of an output of that. In ABC, this will generate this workflow and the folder with 13 different folders, as you can see here, from 1 to 13. Let's check the number 1. This is the first simulation. Inside this folder, you will have the 14 different steps of the simulation, where the last one, okay, which is the step 14, will have the XTC file, which is the simulation at the end, so the trajectory at the end of the simulation. And the same will happen for the rest, for example, number 4 of the simulation. Here you have another trajectory, and you have a trajectory for each of the structures. So the next example is a reduced subset of the protein DNA list, and this is, well, this is the job that I have just presented to you about the protein DNA complexes. From the original list of 50 complexes, we just selected a couple here, but we didn't simulate, in this case, the DNA or the canonical DNA. In this case, we simulate the protein DNA complex, and this is just a test to check the possibility to run protein DNA complexes using exactly the same launcher of the workflow, just modifying the system property and saying that we are interested in working with protein DNA. You can anyway copy and paste that here in our folder. And it has generated a new job, in this case the protein DNA job, with 16 nodes, with 2 different simulations running with 8 nodes in NPI regime. Okay, going to the third example of modeling a set of residue mutations and launching the simulation on a given protein structure. In this case, we are working with a particular mutation, alanine 36927, identified between the angiotensin converting enzyme, and this we are working with a COVID-19, as you can see. Example, the ACE protein in human versus the same protein in the Rhinolopus affinis species, which is bat. This is the mutation from human to bat. 2 MD simulations are running the same job, one for the wild type protein without the mutation, and another one with a model mutation, which is this one. 16 nodes of the MareNostrum supercomputer are used, using 8 nodes per MD simulation in NPI. Now you already are able to identify and to understand the command line. Let me paste here and execute it, and we will take a look briefly now. All of that, you can reproduce that if you want. If you have an account of MareNostrum, you just need to log in, and you will find all of these folders, all the launchers, and the README files with all the information on how to execute these workflows, and you can try it and play it. So this is the wild type structure in this case, which is the human ACE protein. Those are the mutations that I want to model. The first one is I want to simulate the wild type without any mutation, and then I want to simulate this mutation. 5 nanoseconds, 16 nodes, 8 nodes in NPI regime for each of the simulations. Output folder, job name, nothing else that you don't know now. And the job is here, queued to be run using 16 nodes. I will show you an example of the output of this one. This one is the and this human ACE. Again, you have the workflow from the template, the configuration file, modify it according to your parameters, and the launch sh file used in the Slurm queue in this case. You have the folder where the workflow is saving all the results. As you can see here, this is automatically generated by the workflow, the 2 different folders for the 2 different simulations. Let's go to the wild type simulation. Again, you have 14 different steps, where the step 14 is the last one, and you will find the trajectory at the end of the simulation. And the same will happen for the mutated system. In this case, the step 14 will give you the trajectory, but you have the first step, which is the mutation, which will give you information about how we have mutated this, and you have the structure, and you can take a look at the mutation. So far, so good. You can see that it's really easy to launch these simulations. The next example is the same example as before, but now using a custom force field, so a little bit more difficult. This force field was manually modified, the specbond.dat file from GROMACS. If you're familiar with the force fields in GROMACS, you will know that you can modify the distance restrictions here. And we wanted to keep restrictions on a couple of delta histidines with a structural zinc ion in the humanase protein. So now the only thing that has changed here is this particular parameter here, which is the GROMACS library file that points to a force field modifier with the spec bonds. We can take a look at this. Again, this is available to everybody, so you can still reproduce this for this workflow with your user in the MareNostrum. We can look at the spec bonds, and you will find these two modifications here. Especially the last one is the one that we need, 0.24 nanometers, to make the link and the restriction, distance restriction between these the two delta histidines that we have in the structure with the zinc structural ion. So again, we just need to copy this one and paste here to see how the job is queued. This one here, with, again, 16 nodes, same mutation as before, and the only thing that is modified is this GROMACS library. Now I'm changing from the debug queue to the one of the queues that is available for my user, because this takes a little bit more time than the previous one, so it needs another queue because of the limitation of the debug queue, but of course you can modify that. As you know, it's as easy as modifying this QE parameter on the launcher. So the next example is just the same workflow, but using the complex SARS-CoV-2 RBD, receptor binding domain complexed with the humanase, and that is available here just to illustrate you that running all the simulations for the humanase alone and the mutation, and from the RBD humanase complex and the mutation, you can then use this. You can then use the results of these molecular dynamic simulations to compute the free energy. And this is the last example that we have in this README file, computing the effect of a particular residue mutation on the protein binding free energy using this non-equilibrium approximation that I introduced in the presentation. So here you have a lot of information about what I have already explained you in the presentation. This is the actual launcher of the workflow. It seems a little bit more complicated than the other ones, but let's take a look at the command line, and you will see that it's not really complicated. This is the launcher. Again, you can put a minus H at the end, and this will give you a lot of information about all the different parameters, the default values, the type of the parameter, etc. So this is the name of the launcher. This is the mutation that we want to study. And here we have the topology of the wild type, which is just a TPR topology in GROMACS for the humanase wild type. And then the trajectory for the wild type, which is exactly the same, but the XTC trajectory for the wild type for the humanase. And then we have the topology for the mutated system, which is this. This is the topology in TPR for the mutated system for the humanase, and then the trajectory for exactly the same simulation. So we have the XTC file, the trajectory for the mutation for the humanase. Those four files are the input files for the free energy TMX workflow and are produced by the previous workflows that were modeling the mutation and generating, simulating, running the molecular dynamic simulation. So with the previous ones, you could compute this delta T, one delta T. So this is a particular parameter which is telling the workflow that we have two structural ions, so take a look at that and be careful when you generate the index files in GROMACS. This is for advanced users. We are using the index files in GROMACS to identify the dummy atoms that PMX is generating, so we can freeze the rest of the protein and let these ones free. And this is the name of the queue. This is the work clock time, number of nodes, number of frames. That means that 100 frames, we will extract 100 frames from the equilibrium trajectories, and we will run 100 forward and 100 reverse thermodynamic integration simulations. This is in picoseconds, the length of the thermodynamic integration simulations. And this that seems really complicated, it's really easy. That means that the mutation, trajectory has 2,500 snapshots on it. The wild-type trajectory has the same number of snapshots, and the end of the wild-type trajectory is 5,000 picoseconds, or 5 nanoseconds, and the end of the mutated simulation is 5,000 picoseconds, or 5 nanoseconds. This information is needed for the workflow to properly extract these 100 frames from the trajectory. And then we have the name of the job and the output folder. And what this is generating is this type of folder hierarchy. Again, we have the workflow, the YAML file with the configuration, the launch shell script, the workflow folder. Inside the workflow folder, we have two different folders which are called state A and state B. And then we have the last step of the workflow, which is retrieving all the information generated in the different frames and analyzing and generating the histogram plot. I will show you that in a minute, but now let's take a look for a moment to the state A, which are all the forward thermodynamic integration. You can see here, as we have put 100 frames, we have 100 different frames here. Each of the frames, let's take a look at number 7. Each of the frames contain 10 different steps, which are all the steps needed to finally run the thermodynamic integration and to obtain the work values, which are the ones that you can see here. Those values that then at the end are used, the 200 different files, PI files, are used. So here we have the 100 forward, and in the state B we have the 100 reverse, and in the step 11 we have all the results analyzed by TMX. Here is the output, which is applying 3 different theorems. So the Crookes-Gaussian intersection, for example, is giving us the final delta G. The Bennett acceptance ratio is giving us a very similar, in this case, delta G. And the last Jarzynski estimator is again giving us a very similar delta G. It is also generating a plot, which we cannot see here in the MareNostrum supercomputer, but we can open it in our computer. So, this is the plot that is generating. It's exactly the same number. This is the plot that is generated by the PMX using, here you have the 100 forward and the 100 reverse thermodynamic integration work values. Okay, I think that with that, there is more examples. The last one is the same PMX free energy calculation for the complex, and then is explaining that subtracting one delta G from the other, we can obtain the final binding free energy for this mutation on the protein. But it is exactly the same as, and I hope that you could see that it's really easy to run these workflows in the MareNostrum supercomputer. The final step parts of the README, you can find the modules of the BioExcel building blocks that are used in these workflows with all the links to information and the copyright and licensing, which is Apache license 2.0, so really free for everybody to use and distribute. So let me finish with a couple of slides of, one of ongoing projects, just for you to know that we are currently using these Pre-Exascale workflows, using thousands of cores in MareNostrum supercomputer. You have seen that it's really full now. The first project we are working with EGFR, the intracellular tyrosine kinase domain. We are exploring the effect of mutations on drug sensitivity and resistance, with the idea, the goal of to make something like to predict the effect of mutations, different mutations in drug sensitivity or resistance. For that, we are exploring 24 different mutations and 5 different drugs, including erlotinib and gefitinib. We have more than 60 microseconds of accumulated time in the simulation equilibrium simulation for that. We are using exactly the same workflows that you've seen in this presentation. And we are working in another project on the MDM2, MDMX, and P53 PMI peptides. We are trying to reproduce this alanine scanning, the experimental values of this alanine scanning using the same workflows as you have seen. And the most important part of this presentation is that all of this is openly available in the BSC MareNostrum4, so we want you to try it. It's as easy as you have seen to enter into the MareNostrum4 supercomputer with the user account. Just load the Python module and start playing with the launchers of the workflows. You have all the test data already there, so you can play it very easily. We are exploring the possibility to install all of these in different supercomputers. We are now in the CEA in France HPC Center. Also, we are working in the Stuttgart HPC Center and in different place supercomputers. And if you don't have a user in the MareNostrum or the BSC supercomputers, and you are still interested in all of these workflows, please contact us either to Modesto or to me directly. Send us an email. We have the opportunity through the Spanish supercomputing network to try to give you a user account in the MareNostrum supercomputer just to try these workflows and to play a little bit with them. So if you are interested on this workflow, please send us an email and we can work together. We can help you on running this and maybe building new workflows and new interesting workflows for the biomolecular simulation field. So with that, thank you very much for watching the video tutorial till the end, and I hope that you liked the workflows, the pre-exascale workflows that we are developing in BioExcel, and please send us an email if you are interested in having more information. Thank you very much.